There are many shortcuts to high accuracy in medical artificial intelligence. And in this case, taking a shortcut means compromising human welfare. That is why it is vital that we understand these shortcuts and learn how to detect them before they cause real harm. Welcome to today's episode, where I explore one of the most critical yet underappreciated problems in healthcare: artificial intelligence, algorithmic shortcuts. These shortcuts allow machine learning models to achieve impressive accuracy numbers while learning nothing clinically meaningful. By the end of this episode, you'll understand what these shortcuts are, how to identify them, and why strong collaboration between technology developers and medical professionals is vital to addressing this issue. Let me start with a simple scenario. Imagine you're developing an artificial intelligence system to predict which patients have diabetes based on their medical records. You gather data, including demographics, lifestyle factors, lab results, and medication histories. You train your model, it achieves 99% accuracy. You celebrate what appears to be a remarkable success. Then, someone points out that you included a column in your dataset indicating whether the patient is currently taking some form of diabetes medication. Your model did not learn to recognize the subtle patterns that indicate diabetes risk. It learned a simple rule. If the medication column says diabetes medication, predict diabetes. It took a shortcut. And that shortcut rendered your entire effort clinically useless, because if you already know a patient is on diabetes medication, you do not need artificial intelligence to tell you they have diabetes. You would simply look at that column yourself. This is what we call algorithmic shortcut learning. And it is flooding our research literature with impressive looking results that will crumble the moment they encounter real clinical practice. Machine learning models are optimization engines. They are designed to find the easiest path to high accuracy, whether or not that path has any clinical meaning. When your training data contains features that essentially give away the answer, the model will exploit them ruthlessly. This is not a bug in the algorithm. It is exactly what the algorithm is designed to do. The problem is that we, the humans, fail to recognize that we handed the model an answer key along with the exam. Let me give you another example that illustrates this principle with crystalline clarity. Obesity prediction. Suppose you want to build a model that predicts which patients are at risk of becoming obese based on their lifestyle factors. You collect data on diet, exercise habits, sleep patterns, stress levels, and dozens of other variables. You also include height and weight because they are readily available in the medical record. The model achieves near perfect accuracy, but has learned nothing about lifestyle risk factors. It simply learned to calculate body mass index, which is weight divided by height squared. Any model with access to height and weight will trivially learn this relationship and appear to perform brilliantly. But here is the critical question. What do you actually want to predict? You do not need artificial intelligence to tell you whether someone is currently obese. You would simply weigh them and calculate their body mass index yourself. What you actually want to know is whether someone's current lifestyle puts them at risk of becoming obese in the future. You want to identify modifiable behaviors that contribute to obesity risk, so you can design interventions before the problem develops. By removing the shortcut, by excluding height and weight from your model, you force the algorithm to find meaningful patterns in the data that actually matter. When weight values are excluded from obesity classification models, variables like age, dietary patterns, physical activity, and sleep habits become the important predictors. The model becomes useful precisely because it can no longer cheat. This brings us to a crucial concept: data leakage. Data leakage occurs when information from outside the training dataset, or information that would not be available at prediction time, is used to create the model. It manifests in several distinct forms, and recognizing each type is essential for building clinically useful artificial intelligence systems. The first type is target leakage. This occurs when your features are consequences of the diagnosis rather than predictors of it. The diabetes medication example I mentioned earlier is a perfect illustration. Medications prescribed because of a condition, procedure codes that imply a diagnosis has already been made, specialist referrals that only happen after disease is suspected, all of these encode the answer in the question. The model learns to recognize the diagnosis through its consequences rather than its causes. The second type is temporal leakage. This involves information that would not be available at the moment you need to make a prediction in clinical practice. A lab result ordered 3 days after hospital admission cannot help you make a prediction at the time of admission, even though it appears in the same row of your spreadsheet. If your model cannot access that information when deployed in real clinical practice, it cannot rely on that information during training. The third type is proxy leakage, and this is often the most subtle. The feature does not directly encode the target, but it indirectly reveals it. Consider medical imaging. Patients with suspected lung disease may receive imaging protocols specifically optimized to confirm that diagnosis, while patients without suspicion receive generic screening protocols. An artificial intelligence model can learn to recognize the imaging protocol rather than the actual pathology. Hospital unit assignments, specific test orderings, documentation patterns, all of these can serve as proxies that the model exploits instead of learning genuine clinical signals. Now, you might be wondering, if these problems are so significant, why does the research literature overflow with studies that appear to commit exactly these errors? This brings us to what I call the reviewer knowledge gap. The peer review process, which is supposed to ensure the quality of published research, has some limitations when it comes to medical artificial intelligence. Many journal reviewers come from clinical or traditional biostatistics backgrounds. They are experts in medicine, in study design, in statistical inference, but they may not recognize machine learning specific pitfalls. They see 98% accuracy and assume methodological rigor. They do not know to ask whether the data was split at the patient level. They do not think to question whether features would be available at prediction time in actual clinical practice. Meanwhile, reviewers with strong machine learning expertise face the opposite problem. They understand the algorithms, but may not grasp clinical workflows. They cannot spot when a feature represents information that would only exist after the diagnosis the model is trying to predict. They lack the domain knowledge to identify proxy leakage hiding in hospital-specific variables. The result is a systematic failure of quality control. Studies with fundamental methodological flaws sail through peer review because very few reviewers possess both the machine learning expertise and the clinical knowledge needed to catch the problem. Prior studies reveal inconsistent evaluation methods, biases, and a lack of standardization in how medical machine learning research is conducted and validated. This has created what I call accuracy theater. We have built an incentive structure that rewards exactly the wrong behavior. Researchers need publications. Publications need impressive results. High accuracy numbers are impressive. Therefore, researchers are incentivized to achieve high accuracy, regardless of whether that accuracy reflects genuine clinical utility. Journals compound the problem. A paper claiming 99% accuracy attracts attention. A paper honestly reporting 75% accuracy on a properly designed study with leaky features removed, with patient-level splits, with external validation, looks less impressive by comparison. The honest paper may struggle to find a home, while the methodologically flawed paper gets cited and celebrated. The consequences extend beyond academia. When hospitals adopt artificial intelligence tools based on published accuracy claims, they inherit all the hidden flaws those claims concealed. The model that achieved 99% accuracy in the research paper achieves something far worse when deployed on real patients because the shortcuts it learned to exploit no longer exist in the deployment environment. So how do we distinguish genuine learning from shortcut exploitation? The model's training dynamics tell the story. And this is why we need to demand that every claim of high accuracy is accompanied by relevant proof of healthy learning dynamics. Learning curves, which plot accuracy over training iterations for both training and validation sets, reveal the character of what the model has learned. A model genuinely learning complex patterns shows gradual improvement. Accuracy climbs slowly as the model discovers subtle relationships in the data. Training and validation curves converge, but maintain a small gap, indicating the model generalizes beyond memorization. A model exploiting shortcuts looks completely different. Accuracy rockets upward in the first few iterations, often reaching near perfect levels almost immediately. This is not learning. This is pattern matching on leaked information. The model found the answer key and stopped trying. If you see both training and validation, accuracy converging instantly to 99%, that should raise immediate red flags about potential data leakage. Precision recall curves expose another critical failure mode. When your data set is imbalanced, and medical data sets almost always are, a model can achieve high accuracy by largely ignoring the minority class. Other metrics can look respectable even when the model fails catastrophically on the patients who matter most. Precision recall curves reveal the truth. If your model cannot reliably identify the rare disease cases it was designed to find, no amount of accurate, healthy predictions redeems it. Confusion matrices should report actual counts, not just percentages. 98% accuracy means something very different when you have 100 patients versus 10,000 patients. The raw numbers matter for understanding whether the model actually performs well on the clinical task at hand. These metrics should be mandatory in every publication and report. Any document claiming clinical relevance should present learning curves demonstrating gradual, stable convergence. Any paper dealing with imbalanced classes should present precision recall curves alongside traditional metrics. Without these, we are taking accuracy claims on faith. But the problem extends beyond academic publications. The same issues apply to clinics adopting artificial intelligence solutions in the real world. When a chief technology officer and their team develop something for the hospital to use, the medical professionals who end up using those solutions need to know how they were developed. They need to understand the methodology well enough to ask the right questions. This is why we need to train our current medical students on what to look for when it comes to using these technologies. Future clinicians should be prepared to ask critical questions before adopting any artificial intelligence system. First, they should ask, was the data split at the patient level? This prevents data from the same patient appearing in both training and validation or test sets, which would artificially inflate accuracy. If a patient's Monday lab values are in the training set and their Tuesday lab values are in the test set, the model may simply be memorizing individual patients rather than learning generalizable patterns. Second, they should ask, were leaky features identified and removed? Every feature should be audited for whether it would realistically be available at the moment of prediction in clinical practice. Features that encode the outcome, that exist only after diagnosis, or that serve as proxies for the target variable must be excluded. Third, they should ask, what do the learning curves look like? Rapid convergence to near perfect accuracy suggests the model found a shortcut. Healthy learning shows gradual improvement with eventual stabilization. Fourth, they should ask, how was class imbalance handled? For rare conditions, accuracy is meaningless as a metric. Clinicians should demand to see precision recall curves and confusion matrices with actual counts. Fifth, they should ask, was there external validation? A model that performs well on data from one institution may fail completely at another. Performance must be validated on independent data from different sources, time periods, or patient populations. If developers cannot satisfactorily answer these questions, the artificial intelligence system is not ready for clinical deployment, regardless of what accuracy figures the marketing materials proclaim. The solution to this crisis requires breaking down the walls between disciplines. Developers must understand clinical workflows, not superficially, but deeply enough to recognize when a feature could not possibly be available at the moment of prediction. They must learn to ask clinicians, at the point in the care pathway where this prediction would be useful, what information would you actually have? Clinicians must understand machine learning methodology, not the mathematics of gradient descent, but the conceptual pitfalls. They must learn to ask developers, how did you split your data? What features did you include? What do your learning curves look like? This is not about turning doctors into data scientists or data scientists into doctors. It is about creating enough shared understanding that each side can ask the right questions and recognize inadequate answers. We need checks and balances where developers and clinicians hold each other accountable, prioritizing patient outcomes over chasing accuracy numbers for publication. There is also a critical gap between artificial intelligence's robust performance in controlled clinical trial settings and its significantly diminished effectiveness in real-world healthcare environments. Part of this is because clinicians adopting these tools do not know to ask the critical methodological questions we have discussed. The liability implications are also important to consider. Currently, the dividing line for liability appears to be whether an end-user provider could review the recommendations from an artificial intelligence tool and understand how it arrived at them. If clinicians cannot interrogate the methodology, they are flying blind and potentially liable. The ability of healthcare professionals to trust technology and understand how it benefits patients is critical for adoption. But trust should not be blind. Instead of focusing solely on the clinical application of artificial intelligence, our educational frameworks should be more concerned with educating both the technological creators and the clinical users. The problem of algorithmic shortcuts in medical artificial intelligence is not unsolvable. It requires vigilance, education, and a fundamental shift in incentives. We need reporting standards that mandate transparency about feature provenance and temporal availability. We need reviewers with hybrid expertise who can evaluate both algorithmic methodology and clinical realism. We need journals willing to publish rigorous negative results when models fail to generalize. We need medical curricula that prepare clinicians to be critical consumers of artificial intelligence tools. Most importantly, we need to remember what we are actually trying to accomplish. The goal is not high theoretical accuracy. The goal is improved patient outcomes. A model that achieves modest accuracy while genuinely learning from clinically meaningful features is infinitely more valuable than a model that achieves spectacular accuracy by exploiting shortcuts that evaporate upon deployment. There are many shortcuts to high accuracy in medical artificial intelligence. And in healthcare, taking a shortcut means compromising human welfare. A model that learns to cheat will fail when cheating is no longer possible. A 99% accurate model that relies on information unavailable at the bedside is not a success. It is a liability dressed in impressive statistics. The patients whose lives depend on these systems deserve better. They deserve artificial intelligence that has genuinely learned to recognize disease patterns, not artificial intelligence that has merely learned to exploit data artifacts. They deserve clinicians who can critically evaluate the tools they use and developers who prioritize clinical utility over publication metrics. The shortcuts are everywhere. Learning to detect them is not optional. It is an ethical imperative. My name is Dr. Toma, Associate Professor at the New York Institute of Technology, College of Osteopathic Medicine. For those who want to explore these concepts in comprehensive detail, I've written a 2-book series, Diagnosing AI and AI-Assisted Medical Diagnostics, which cover everything from foundational principles to practical implementation guidelines. Thank you for listening.